In this video, we're going to look at polyprotic acid strong base titrations. So remember, our polyprotic acids were acids that had more than one proton that it can lose, so more than one ionizable proton. And remember, when we talked about them previously, we said that each proton ionizes in its own step, right? So if I had H2A, I could react that with water, and I would go to hydronium ions plus HA, right? Its conjugate base. So it has two protons, but it's only going to lose one of them. And this reaction is defined by Ka1. HA minus then can also react with water to produce another hydronium ion plus A2 minus. This reaction is defined by Ka2. Because I can lose two protons, we're actually going to have two equivalence points, right? We can write two neutralization reactions. One where H2A reacts with our base, and then once all of that has been neutralized, HA minus can also react with that base. So we can have two equivalence points for an acid like this. This one's diprotic. If you had an acid that had three protons that you could lose, you would actually have three equivalence points. So for every proton that your acid can lose, you're going to have an equivalence point. And we're going to look at this conceptually. So I'm going to draw a titration curve here. So pH increasing on my y-axis, volume of base added increasing on the X. And we're going to go up in pH, right? We're going to start out acidic and then kind of level off like we normally would do, but then it's actually going to go up again and then level off again. So I'm going to mark our points on here. So we're going to have number 1, that's initial like just before. Number 3 here is going to be my first equivalence point. So this is going to be number 1. This is going to be number 3. And then everything between number 1 and number 3 is going to be number 2. I'm going to have another equivalence point here. We're going to call this number 5. And then everything between 3 and 5, we're going to call number 4. And then everything after number 5 is going to be 6. So number 1, right? Number 1, all I have is H2A. So H2A only. And again, we're just looking at a diprotic acid. So you would calculate the pH as you would for any diprotic acid. Remember that first reaction was my principal reaction, so we can determine our pH using only Ka1. Right, my first reaction was that principal reaction. Number 2, we're actually going to have a buffer solution, right? We're now adding base to it. If we go back down a little bit, I'll scroll back up, I promise. So I have H2A, I'm adding base to it. We're producing water plus HA minus. Right? And then I'm going to make up numbers here. Let's say I started out with 0.1, and actually let's use millimoles. Let's say I start out with 10 millimoles of this. And then at the equivalence point, at number 3, we would have 10 millimoles of base also. We're below that equivalence point, right? That's at this point that we would have 10 according to my numbers here. We're below that, right? We're to this side of 10, so I have less than 10. So I'm just going to pick a number and let's make it half, let's say 5 millimoles, right? Since we're below that first equivalence point, we have less number of moles of hydroxide ions than we do H2A. And then when we subtract the smaller from both of those and then add to the other side, right? My base has been neutralized. And if I look at this change table, right, what we have is I have an amount of H2A and I have amount of A minus. Those two are conjugate acid base pairs, so I have a buffer solution, right? And specifically, it's an H2A, HA minus buffer solution. So at point number 2, we have an H2A, HA minus buffer solution. You can use the Henderson-Hasselbalch equation if you want to solve it. The pKa that you plug in would be pKa1. And if it's halfway to the first equivalence point, then your pH is going to be equal to pKa1. So if the half equivalence point pH equals pKa1. And that's what my example down here is, the half equivalence point. I actually have equal amounts of this. You would have to change the concentration by dividing by the volume. The same with this one, but they're in the same container, so they're going to have the same volume, which means they're going to have the same concentration. And when I take the ratio of my base over my acid, it's going to be 1 because I have the same values. Log of 1 is 0, 0 plus my pKa is just my pKa. So point number 3. Point number 3 here is my first equivalence point. And my pH at our first equivalence point is actually the average of my two pKa's. So my pH is going to be pKa1 plus pKa2 divided by 2. And this is actually called the isoelectric point. If you go on and take biochemistry, you are going to look at titration curves for amino acids and you will use that term. So isoelectric point. We won't really use it so much here. I just do want you to have heard that term before. So looking back at our neutralization reaction here, right? At my first equivalence point, so point number 3 on that plot, right? Moles of my acid are equal to my moles of base, right? That's the definition of my equivalence point. So when we subtract these, right, both of these are going to 0. We then added it over to this side, and I have the 10 millimoles of HA. So what we're doing now is we're continuing to add base, right? We were at this point, I'm still adding base. So this point here, we're actually now on our second reaction, right? All of this has been neutralized. So when I go to write my neutralization reactions for anything after that first equivalence point, it's going to be the reaction between HA minus plus my hydroxide ions, right? These are both 0. So when I add more base to it, it can only react with this because I don't have any more of this. So I have HA minus plus hydroxide ions going to water plus A2 minus. And then kind of looking at our numbers again, I have 10 millimoles of this one, so I'm going to bring that over here. And then again, At the second equivalence point, at 0.5, right? That's going to be my second equivalence point. Moles of HA are going to equal my moles of OH minus. We're not there yet, so I'm going to have less OH minus than I do HA minus. So I'm just going to pick 5 again, but any number for my example here less than 10 is going to work. This is 0. I subtract 5. Subtract the 5, right? Always subtract the smaller of your two reactants from both reactants. This goes to 5 millimoles. This goes to 0. Add to this side. And then when we take a look at what we have, right? I have HA minus and I have A2 minus. Those are conjugate acid-base pairs, so I have a buffer solution. So this time though, it's going to be an HA minus A2 minus buffer solution. So 0.4, it's going to be an HA minus A2 minus buffer solution. Again, you can use the Henderson-Hasselbalch equation, but this time you do need to use pKa2. And then if you're halfway to the second equivalence point, which we are in my example, right, the amount of HA minus that I have is the same as the amount of A2 minus. My pH is going to be equal to pKa2. And I'm going to run out of room, so I'm just going to slide this stuff down a little bit. Oops, I didn't mean to turn it sideways. Just meant to get it out of our way. Sorry about that. Number 5. Number 5 here is our second equivalence point. This time, right, if we scroll back down, kind of moved out of the way a little too much, right? At that equivalence point, my moles of hydroxide ions are equal to my moles of HA minus. So this would be 10 also, right? Subtract 10 from both sides. These guys, sorry, from both reactants, those are both 0. And then when we look what we have, right, I don't have any HA minus, I don't have any hydroxide. What I have is A2 minus, which is a weak base, right? It can react with water to form hydroxide ions. So we would write our base dissociation equilibrium equation similar to what you would do at the equivalence point, or the only equivalence point for a weak acid strong base titration. Right, all of my acid has been neutralized. My first proton I can lose, right? This has all been neutralized, and then this has all been neutralized. So all we have left is our weak base. I'm back up to write this. I have A2 minus only, right? And essentially you're going to use Kb, but you need to get that Kb that you're going to use from Ka2, right? If we go back up and look at this, Ka2 is the one for the reaction that involves A2 minus. So you need to use this Ka2, divide that into Kw to get the Kb that you need for this step. So it's a weak base solution, right? You're going to use Kb, but get it or calculate it from Ka2, right? That's the one that involves A2 minus. And then one more point for us number 6. So going back up, right, number 6 is everything after that second equivalence point. At that second equivalence point, remember we have neutralized all of my acid, right, H2A. That was all neutralized at my first equivalence point. And then HA minus has all been neutralized at my second equivalence point, but we're still adding base. So at this point, all we have is excess base, right? If we went back down and looked at these numbers again, right, this time I'm going to have more base, right, more of this than I have of this, right? Those two numbers were equal at the equivalence point, but I kept adding base. So I now have a larger number for my hydroxide ions. So let's just pick 15. You didn't change this. This is 15. Sorry, goofing this up on you. So 15 millimoles of hydroxide. Subtract the smaller, which is 10. So this goes to 0. I have 5.0 millimoles of hydroxide ion left over. You would add it to this side, but just like we were doing with weak acid, strong base titrations, the amount of hydroxide ions that you're getting from this weak base is really negligible compared to the amount that you're going to get from this strong base. So you can just kind of ignore this part and only focus on the hydroxide ions. So it is excess strong base. And again, this is just a diprotic one. If we had triprotic, right, I had 3 protons that I could lose. So something like phosphoric acid, H3PO4, I would actually have 3 equivalence points. And you would just kind of keep this trend, right? If I had 3 protons at the beginning, it would just be a weak acid solution. So H3A. Point 2, it would be an H3A, H2A minus buffer, right? This point, the pH would be the average between pKa1 and pKa2. Here I'm going to have an H2A minus, HA2 minus, sorry, that's so confusing, buffer solution, right? And just kind of keep going. Your next equivalence point would be the average between pKa2 and pKa3, and so on. So you could scale this up for a different amount of protons.